Okay, good afternoon, everyone. I'm Gavin from Malaysia. I've actually been a Perl, shell script, Java, and now Python developer over my career. And so recently I've been looking up at, reading up on functional programming, and this talk is basically encapsulation of what I've learned. Obviously, it's a bit hard to do functional programming in Python, but it's just something as an academic exercise, okay, and you can learn a lot from it. So I think we should start on the next slide. So I planned for 30 minutes roughly. So I think I should be able to meet that and try to stay on time. So let's start off with some motivations. First one is a quote from Tim Sweeney from a presentation that he gave on the next generation. Sorry? Take the mic. Okay. So this first quote is from Tim Sweeney, and he's actually a game developer or in charge of a game company. In his presentation, so he says that functional programming is the right default for the next generation of programming languages. And what he means by explicitly effects typing constructs is basically moving programming constructs that actually do side effects into a specific place, so you can, when you look at the program, you know where that happens, rather than mutating variables or state everywhere in your code. Okay. And recently, John Carmack from ID Software also wrote a blog post about doing functional programming in C++. He's in this blog post, he basically wrote about the virtues of pure functions and things, and is basically considering about, for example, moving from C++ to a more functional system-level programming language like D or Rust from Mozilla. Okay, onto the functional way. This is a very general overview of specific properties of functional programming style. So the first thing that is characteristic of functional programming is pure functions. Typical example are mathematical functions, in which you can put in a parameter to the function, and you can call it multiple times, and it's going to give you the same result. Okay. What's good about this is that you can compose pure functions, and you don't really care about the order of execution. So, and the function could, a particular function could accept multiple pure functions, and in effect, it doesn't really matter. What you want is, in the end, when you're evaluating that pure function, you want the value of that function, right, or the value of the functions you passed into. So because the execution order is insignificant, concurrency is not a problem. It is side effect free. Programming languages that are functional encourage you to use immutable containers, so that you don't accidentally go and mutate the state. And in a way, you can think of functional programming as doing data transformation. So you have a piece of structure which contains data, and you're transforming it to another form. So I don't know if any of you have done XSLT transform, but what it does is it basically transforms XML from one form to another, and that is a very good example of what functional programming does, right? So imagine transforming XML to HTML, for example. Functional programming languages also prefers recursion over iteration. they basically don't have looping constructs that we're used to in, for example, in Python, in for loops or while loops. They encourage higher order functions, which are basically functions that take other functions or return functions. And this is usually available in languages that provide functions as first-class values with closures. And some functional programming languages emphasizes lazy evaluation, which means that that particular expression are not immediately eagerly evaluated. I'll explain a bit more of it later on. And there are some other functional characteristics which I'll not list here. Just get to be fast. So is Python a functional language? It is not. It's basically an imperative language, a language which has acquired some functional features over the years. Okay, some of them are listed over here. Lambdas, or anonymous functions, with functions without names, and then we also have the map, filter, and reduce functions, which are common in other functional programming languages. We have the iter tools module, which is basically for effective iteration over sequences, and functools, which are a collection of functions which operates on other functions, and in Python's case they can operate on callables, anything that is a callable. Okay, so this is just a potpourri of stuff. So there are some immutable containers which we have in Python are like tuples and frozen sets. Lists and dictionaries are obviously immutable, so I mean you pass that into a function that somebody wrote, and they could mutate the data inside. There's obviously a severe limitation in lambdas. That's something that I think most Python developers know, that you can only do them. You can only write a single expression, right? Unlike other languages. While I was teaching myself functional programming, I basically used Haskell as the language, as the base language to compare with Python. And one of the things with Haskell is that it's a static typing. It has static types. Okay, so types everywhere, unlike Python. But it is not something that would slow you down, because it has a very good type inference built in. So it knows if you don't put a type in it, you'll put a default on top of it. Okay, so just a quick introduction to Haskell. This is a type signature for a function. So every function will have a type signature. So it's just not, you're not just talking about values. So this is a function called sum, which basically takes a list of some type and return this, a single value. Okay. If you were at the keynote where Alex Martelli was talking, this is called the type class, which is basically saying this A here, this is a placeholder for something which is numeric. Okay. And also, while teaching myself Haskell, also found there's one thing that's not in Python, which is pattern matching, and this is a feature of the fact that they have static types and also something called algebraic data types. So this is not something that you can easily replicate in Python. And pattern matching here, it doesn't mean regular expressions. Okay. So other features of, just a quick overview of the common features in functional programming are, as I've mentioned, are higher order functions. which basically functions which take functions as arguments, because they are first-class values, and they can also return functions. So the map is a built-in function in Python, in which you can pass a function as the first argument and a sequence, and what it basically does is equivalent to creating another list, but applying that function onto every item in the list. In Python 3, map returns an iterator. In Python 2, you'll have there is a function called imap in itertools module, which will return an iterator. Next, you have filter. Filter just takes a predicate and a sequence, and then based on that predicate, it will create a new list, and every item in the new list basically satisfy that predicate. And reduce, we will look at that in detail in the upcoming slides. Any questions at this moment? Yes?
So are you mixing 2.663 along, or is this just
Sorry, can you repeat that?
so you made a reference to Python 3.x.
Uh-huh.
So just for my curiosity, does that mean rest everything is just 2.
Oh, sorry. Yeah, I should state that. So basically everything here is presented for Python 2, Python 2.7, and wherever there is an exception, I will point it out as like for Python 3 and so on. Yeah. Sorry.
Yeah. The filter.
Uh-huh.
Can I see that earlier slide? Map and filter. Can't you emulate filter in terms of map? The predicate to be a function. How is it different?
I've never thought about that, but no. What happens is that in map, if you pass in a function that returns, there is a predicate, so the predicate returns true or false, right? So if you pass in for map, you end up with a sequence of true or falses, which is not for map.
For map.
Yeah, which will not be, which is different from filter, because filter will return to you a list of sequences that satisfies that predicate, only satisfies that predicate. Yeah, so it's different. Okay, so as you know, we have list comprehension in Python, which allows us to basically, in a way, replace filter, right? The filter function. This is basically inspired from Haskell, and Haskell was inspired from the set theory notation. Okay, so this is how you would create and filter lists. Yes, as I've said, so there's actually no reason for to use the filter because you can do the same thing in list comprehensions. Okay, so we'll move on to the next big item in my talk is recursion. So as I've said, functional languages do not have for loops, while loops, basically those constructs for iterating through sequences or dictionary keys or something like that. So what do they have? They will have, they prefer you to use recursion. Well, not prefer, that's the only way they can do it, right? The only way they can do iteration. And when you're doing recursion, you'll be using a lot of the stack, right? You're creating stack frames. So here's a naive sum function. It's naive because it's not something you would do in Haskell, right? But this is just for our discussion. So again, there is a type signature for the function, all right? And here's pattern matching in action. So we say if I pass in an empty list, it returns 0, the base case, and this basically matches a list, a sequence in Haskell, in which X is the first element, okay? And then this is the rest of the list. And so what this does is basically it sums up all the items in the sequence. All right. And if we were to replicate that in Python, this is how it would look. Again, very naively, right? The base case, and then the recursive part. Okay. This does not work if you pass in an iterator, for example. Because this assumes that I can index through the sequence. Okay. And we will fix that. So when we run this, if we go, we trace through the execution, what you see is that you can see the recursion going on here, right? And then here is returning back from the recursion until you get to a value. Because you have to maintain all these intermediate values before you can do the operation, you need to maintain stack frames, okay? And the thing is that stack frames are scarce, right? By default, we have 1,000 stack frames on the C Python, and if you pass in something that matches that, you get a stack overflow. Okay, so if you're doing recursion naively, this is not going to work in Python. We can improve this further by doing something called, by changing it to be tail recursive. So basically what it means, tail recursive means that the final call is actually the recursive call to itself. Okay, so these are examples of non-tail recursive calls, because here, although we're calling the function itself, but there's a multiplication that needs to happen there. And here, naive sum function, we need to do an addition at the end, right? So a very old technique is to use an accumulator argument to make it tail recursive. So this is the Haskell version. So we're not just accepting the sequence, we're accepting an accumulator, right? And what we're doing here at the end, as you can see, we're just calling sum with 2 parameters, the rest of the list, and then the value that's been accumulated. So functional languages like Scheme and so on, they actually allow unbounded number of active tail calls, unlike what you saw with Python when you get a Stack Overflow. How it does this is that it reuses the stack frame. The first stack frame that was used, it would just change it. So it's just reusing it but basically changing the arguments for the stack frame and then re-executing it. So this is an optimization, okay? I wouldn't go into how Haskell does it. It is a bit more complicated than that, rather than reusing stack frames, partly because it's a lazy language. So by converting that function, that naive function, to tail recursive version, what we're doing here, as you can see, is the last call that is returned is actually the recursive call, okay? And there's just with 2 arguments. And we start off the execution by passing 0 in this case, because this is what we want to accumulate. So this is a 0. Unfortunately, Python does not do this kind of optimization, and Guido has objected to this. I think he has published 2 blog posts about this in 2009. Okay. So one of his objections is that if you were to optimize this away, you will not get useful stack traces. So if something happens, you just, it's not going to be useful. So that's an end to that. So what else can we do? Since we cannot have unbounded recursive calls, well, I would say because of the limitation, prefer iteration over recursion. In our example, there's no point in writing that recursive version because we can use the built-in sum. as much as possible, avoid the Python stack or manage your own stack. And one of the techniques to manage your own stack is something called trampoline. Trampoline is like an executor, right? So what you're doing is, and it works for tail recursive functions. Okay, so you need to convert your recursive function into a tail recursive version. And how it works? Okay, let's go through this. I took this from something that James Tauber. This is an example that he gave. So the first thing you do is that you create something called a thunk. Okay, so a thunk is a. If you were to run this, right? If you were to execute this, will execute immediately. Okay, so by creating a thunk, what you're doing is that you're passing in the function and the arguments, and this is actually not executed, right? This is actually not executed. So you're basically delaying the computation. Okay, so then in the tail recursive, the recursion, what you do then is you don't return the evaluation of the whole thing. So you are returning the thunk, which accepts the function and then the rest of the arguments. Okay, so this is the recursive part. This is the base case, right? This is the base case, which I've converted so that it will support iterators. And we can simplify this further. If you're using Python 3, you can unpack the iterable like that, so that this will be the first element, this is the rest of the iterable, and everything is the same. And this is how we would write the trampoline, right? So I'll explain this in detail. So basically, you're basically passing the first. You're not passing the function, so you're passing the thunk. Okay, so you're passing the thunk, and it checks. If it's a thunk, it will execute it, right? And once you reach the base case, it's going to fall out from this this check here, and then you get the value. Okay, so this is a graphical version. So the orange part is every time you do a callable here, a callable check, right? So if it's a callable, you'll execute it, so it'll bounce. Okay, it'll bounce, and you do this until you return the value. And when you land, that's where you get your sum. Okay. So how would we start the trampoline process? You pass in the thunk or the tail sum, the sequence, and the initial value. Okay, for the recursion. And by doing this, I can like just as an example, I can do I do a sum up to 2000. Although I didn't change the recursion limit, it's still 1000. Okay. However, doing this is slow. Okay, it's really slow. It's just an example. This took 1.66, and but the built-in sum function took that. So it's really slow. Okay, so highly inefficient. So in a way, if we want to do recursion properly in Python, we need optimization help from the bytecodes or from the interpreter itself. Okay, so any questions? No? Okay, so next going to another big topic. It's called Cattlemorphism. Now, obviously when I started learning about this, it's all very scary because no matter how much I try to read up on all these mathematical concepts, I mean, you just like go round and round in loops, right? Because there's too much reading to do. Okay, so don't be afraid. Don't fear this thing, because we're just gonna skip over this thing unless you're the mathematically inclined type of person. Cattlemorphism is just a general idea that describes folds. Okay, folding. Remember, in one of the initial slides, we had three high order functions: map, filter, and reduce. Okay, so folds are basically reduce. Okay, they're equivalent. What does it do? Fold encapsulates the recursive pattern of processing data structures. So as you see in my previous section on recursion, the recursive code is actually, there's a pattern to it, right? There's a base case and then there's a recursive case. When in this case we're talking about processing lists or sequences, so there's a pattern going on, and somebody has identified this pattern, and basically the for, what it does is take a sequence and reduces to a single value. So when we're doing sum, that's what we're doing, right? We're just summing all the items in the sequences, and we return, what do we return? A value. So we've seen this. Okay, so as an example, we'll just take this function, the sum function again from Haskell, and we can convert this function so that I can explain it better into the plus in Haskell can be used as a prefix operator. So in this case, it's an infix, right? To make it a prefix operator, all we do is just put in brackets around it. So now we can use it in that prefix position, okay? So a fold has something called a universal property, okay? The universal property says that whenever you have a pattern like this, it is actually equivalent to calling the for, okay? So you have basically collapsed all this code into a single line of three items, right? And if you're interested in the mathematics and the proofs about this, this is a very good paper to read up on it if you have time. And I want to emphasize that the f function here, the f function, which is the plus operator, takes two arguments. Arity means takes two arguments, okay? And we're talking in this case about finite lists, not infinite. So basically sum in Haskell, you can just do this. You don't have to write the recursive code at all. You can just do this, and that's it. And because it is mathematically equivalent, all right, it's clearer, it's short, the code is shorter, and you're not going to make any stupid mistakes. So yeah, I should show. The thing here is that I want to emphasize is that in Haskell there's no such thing as a for operator. This is in a mathematical concept. They have something called for L and for R, because there's actually two ways to do a for, okay? You can do it folding from the left, and you can do it folding from the right. So if I'm, for example, here I want to find the length of a sequence, what I can do, this is a lambda in Haskell, right? It takes two arguments. The first argument will be our accumulator, okay? So it's going to, when we call this, 0 will be the accumulator, and x will be any one of these in the sequence. So I can show you it in a graphical manner. So when you run this, the first thing that happens is that the function f will be applied, or the lambda, the function f will be applied to two arguments, 0, the best case, and then the first item from the sequence, which is 0, and so on and so forth. So this is called left for, okay? And the right for is the mirror image of that. In Haskell, you will see that again, the accumulator has now moved over to be the second parameter, second argument of that function. And if we run this, this is how it would evaluate. So this is called the write for. Okay. So the point is, the only thing that you need to take from this few slides is that whenever you want to write a recursive function that basically reduces the sequence into one single value, you can just use the for. You don't have to repeat you don't have to write the recursion function yourself. So there's no such thing as a for L and for R in Python. We have reduce, and that's the Python version, and it doesn't. Then there's no left and right for versions of that. So basically, you have to use the single function for both. So here's an example of reversing a list using the reduce function. Pass in a sequence, and we're just inserting the item to the front of the list of this accumulated list. So we start off with passing the base case, which is an empty list, and as it goes through, it will push it to the front of the list. So here's a quick example of implementing Haskell's elem function using the write for. This example is so we want to use the write for to implement this in Python. Okay, so all it does is just like it basically does in Python, one in sequence. All right, to check for the existence of the item. And so this is in Python, right? The only different from, because we're doing it we're doing this in using write for, we have to reverse the sequence, okay? Because we're starting up from the end of the list instead of the front of the list. In Haskell, it's done automatically, right? And here we try to maintain the match the method signature for the lambda in Haskell. So accumulator is on the right, right? So what do we do here? And because the accumulator is on the right, we have to swap it over here. Okay. So we start off with false as the base case. That is to say, this item does not exist in the sequence. Okay, so that's our initial value. And until a match is found, once there's a match is found, that accumulator becomes true and stays true. Okay. In terms of the performance, it's not too shabby, but it's still slower than the. So here I'm not doing the elem. I'm testing this with the addition. Okay, the summing of the sequences. It's not too far off. In Python 3, reduce has been moved to functools. I mean, just and there's some other things to note is that reduce in Python does not short circuit. It will apply that function to every element, no matter how long that sequence is. So if you try to do this, it will not short circuit. Similarly, so this is trying. You'll be better off doing an any here, or in this case, do it all. And you can implement map and filter using reduce. So I'll leave that as homework. How much time wise? 5 more minutes left. Okay, well then I won't finish it then. Any questions up to this point? No? Okay, since I only have 5 minutes, then I should be just cover this section. Okay.
Just wrap up and then we question answer.
Ah, okay, okay. Then should I cover this section or go to my last slide?
Ask the audience. Just go on.
Go on, just go on. Okay. So there's another feature here is about currying. I'll be as quick as possible. It's a technique for transforming a function that takes multiple arguments into a chain of unary functions. Okay, so unary functions means a function that take one argument. For example, if you want to curry a function that takes two arguments, something like this, what you would do, you can do this manually by using the lambdas. I think you've seen this in the when we were writing the thungs, okay? And when you do this, when this function has been curried, you cannot basically pass all the arguments at the same time. You have to pass it one at a time. Okay, so we're passing one to the curried function, which means that it's going to return us this with a filled in, and then when we pass in 2, only then f is evaluated. Okay, so that's the whole point of currying, and you can do uncurry as well. So if you have a curried function, you can uncurry them manually like this. In Haskell, all functions are curried, so you might think that all of them are accept multiple arguments, but implementation-wise, they are by default curried. So when you are looking at a type for a function, you might read this as taking 2 arguments and returning another argument. But actually, it takes 1 argument and returns a function that takes 1 argument and returns the return value. Okay. So this would be the uncurried form if you were to pass in 2 arguments. So what's the point of this? For mathematicians, it's good to be able to treat functions uniformly. So basically, all functions accept 1 argument and return 1 argument. Okay. From a practical point of view, you can create what's called partially applied functions, which you have already seen in my example. So what it means is that we want to bind some values to some arguments, but we don't want that function to be evaluated yet. Okay. So in this case, as an example in Haskell, this is a multiplication operator, but and what it does is that we're saying we want to multiply 2 to all the arguments. Okay, but obviously this multiplication operator takes 2 arguments. So here what we've done is that we're passing a partially applied function. So in Python, we have something called a partial object, which actually provides the ability to create partial applications to partially apply functions. For example, here I've performed the subtraction. Okay, so this is what we've done here. We're saying the first argument takes 1, so when we pass in another argument, we're doing the subtraction like this. So the thing about the operator module is that it's written in C, and because of that, you cannot bind it to specific positional arguments. But if you write your own functions, there's no problem. So in this case, what I'm doing here, I'm binding it to B instead of A. I'll skip this. And partial can be applied to classes, class methods, instance methods, not just to a normal function. And it can be you can create thungs with that, and I won't go into that. So so basically the next few slides are basically looking at some of the functions in functools. I think I can skip that. So basically this last section is a case study of an application of high order functions to create basically a parser. I'll probably skip this. This is basically just an example of parsing a very simple example. Now you shouldn't parse it like this, but this is just an academic exercise. Okay. So I will do this. And in the end, I certainly think that learning functional programming can make you a better programmer. We all struggle with state changes, and especially in concurrency, like who made this change, and trying to trace bugs. So when you are able to isolate the particular parts of your application that does side effects, it's much easier to track bugs. And my conclusion is that in order to be good in functional programming, you have to know a lot of math, and so you have to learn category theory, type theory, and all these things. So if you just graduated from university, I think this is not a problem for you. But for other people who've been out in the industry, they'll have to revisit all that math. Not sure if it's possible actually. Don't have time. I would say that to be it's good to be able to play with other functional languages. So Haskell, I think, is if you want to be good, you need to get into that. OCaml is another good language. It's a hybrid. It's a hybrid of imperative and functional, and JavaScript, which is it's not really a functional, but it is also a hybrid like Python. But it's probably closer to Python because it's dynamic. It's dynamic types. Okay, unlike Haskell. So perhaps the most the best thing you could do is to pick up this book or follow the course online. This is the SICP, which is the wizard book, which will teach you a lot about functional programming concepts and applications. And that's it. Thank you very much. So, is any questions from the crowd? Yes.
Talk about curriculum. So just want to trying to understand the I understood correctly. Suppose I have a function call which is taking 10 arguments. Right? So if I do that, it would mean that I am going to make at least 10 function calls more. Correct? It's a one-to-one mapping, right? Since you want to make it
One argument, take one argument. You don't have to manually create it like what I did with the lambda. You can use the partial.
exactly.
Yeah.
So suppose I have code generation inside, which figures out how many arguments are there.
Okay, okay.
But eventually I have to create 10 more functions, right? I have to make 10 more calls, right?
You don't make, well, when it's executed, you don't make 10 calls. It's just going to be executed by the interpreter as one call.
So the stack
They just
frame,
accumulate the arguments.
okay,
Yeah.
So on the stack frame,
Oh, stack frame. Okay.
yeah. If we have 10 function calls, why it's still
No. That function was never executed in the first place. It's just hanging there. It's like waiting for all the, because like, let's suppose it takes 10 arguments and you've only passed in 8 arguments. That function, if you try to really run it, it's not going to work, right? It's still expecting 2 more. So nothing. There's no stack frame was created for them.
let's assume that there
Yeah.
are 10, what happens?
If there are 10 arguments and you pass in 8.
No, I passed 10.
Oh, you passed 10.
Yeah. So what happened? How many?
So one stack frame.
One second.
Yeah.
That means I didn't understand.
Oh. Okay. Any more?
I'm just curious, what made you go into functional programming from Python?
Oh, why do I want to go and learn this?
We started programming in Python, then you went into functional programming.
Okay.
Then there's like Haskell, which I
Oh,
think
okay,
most
okay.
stick to.
Yeah. Well, yeah. I could have stuck to Haskell, but the thing is, the pleasure of programming in Haskell means that when I go back to Python, it's like you're missing something. You feel like, I like it doing there in Haskell, so I still want to do it in Python. But obviously, in this case, there's a lot of trade-off. Like in this case, the performance is not very good, right? So when there's the right problem that fits the functional style, then I would do that. But for performance-wise, that would be a problem.
So does that mean you are able to identify a set of problems that will be more suitable for functional programming, but Python is not able to?
No, you can do the same thing in imperative. Right? Whatever
Yes, correct.
whatever code that you can do in imperative, you can do in functional, right? As you can see, the functional way is usually, in most cases, shorter and very succinct. Like, okay, in this case, list comprehensions, for example, right? Is in Python, but it came from Haskell and so on, right? So Python has been absorbing all these things, right? It's just like any other languages. So you know, obviously, if you work if you're programming in Python, there are so many things that are available to you: generators, the list comprehensions. If those things fit your can help you solve your problems, and you don't need any other functional ideas, then it's fine. Yeah. Okay.
Are there any other questions?
All right.
If not, let's convene for a break now. The next, so we have a tea break until 4 o'clock. At 4 o'clock, you can go for Vim as a Python IDE at this room, or Python Django web development at E4, or 4C, Pythoning the Indian engineering education at E5. Thanks.
Thank you.